So thank you for inviting me to give the keynote on this important conference. I'm going to talk about intelligent architectures for intelligent machines. This is actually a much longer talk than the time is allotted for, so let's see how much we can cover. So I'm going to go relatively quickly and probably skip a lot of slides, but please let me know if there are questions. Feel free to stop me also if needed. Today, I think we all know that computing is bottlenecked by data, and data is key for many important applications. All important workloads, AI, ML, genomics, whatever you can imagine is data intensive. And they require rapid and efficient processing of large amounts of data. And data is on top of this increasing. We can generate more data than we can process. And these are some workloads that we're used to, more or less, that are bottlenecked by data and that constrain our machines, actually overwhelm our machines, in my opinion. And these are some other workloads that also we're used to on the mobile side that overwhelm our machines. But there are some emerging workloads that are very interesting also going into the future. This is an example from the genomics domain. Today, we can generate genomic data much, much faster than we can actually process it. And this is aided by some of the genome sequencing technologies that are really interesting going into the future, that are high throughput, that are actually scaling much better than Moore's law has helped us in the computing domain. And as a result, sequencing devices are getting a whole lot better, but we're really bottlenecked in the computation part to enable scientific discoveries going into the future, as well as medical advances. And today is a special time with COVID-19. These technologies are being heavily used. But this is just an example from the bigger scientific domain. There's a lot more to do in different scientific areas. I'm going to focus on genomics a little bit because it's some area where we have been focusing on quite a bit recently. And we've been looking at these devices that can generate data much faster. But if you look at these devices, because they cannot do computation inside them, or their computing paradigm is essentially based on processor centricity and moving data all around the world, as well as inside the device and outside the device, we're basically bottlenecked by data in terms of performance and energy. And I don't have time to talk a lot more about this, but we recently written a survey paper on this topic that we're working on. There are really interesting directions that are more data-centric, data-driven, data-aware, like what I'm going to talk about today. And this is one of the recent works that we published at Micro that develops a approximate string matching accelerator specifically for genomic analyses, but it could be used for other analyses as well, since approximate string matching is very useful in many domains. So data today overwhelms modern machines. It overwhelms the storage and memory capability, communication capability, and computation capability in the end. It also greatly impacts robustness, energy, performance, and cost. If you go back to the fundamentals, a computing system consists of three key components: computation, communication, and storage and memory. And we've heavily optimized the computing unit for a really long time. We still have a lot more to do, of course, but comparatively to the communication and memory and storage units, we've put a lot of effort into the computing unit over decades and decades. And it's the only place where computation gets done. And all of the other places in the computing system, broader computing system, are essentially dumb. They don't have the ability to process anything they see, even though they see much more data than the computing unit sees over their lifetime. So basically, because we have a processor-centric design, most of our systems look something like this. This is my cartoonish picture. If you look at this picture, the computation elements, the red parts over here, are the cores, and everything else is there to serve the core. Essentially, it is there to store and move data for the cores, for the accelerators, etc. And if you do the calculations, less than 5% of a single node is including all of the parts of a computing system, is dedicated to doing computation. Everything else is there to dedicated to storing and moving data. Maybe we should be calling these devices storage and data movement devices as opposed to computing devices. So as a result, data overwhelms modern machines. And recently we did this work with Google where we analyzed these key workloads that I showed in the previous slide. And we found out that more than 60% of the entire system energy is spent on data movement in these workloads. We're going to get back to this work later on. So my axiom going forward will be that intelligent architecture has to handle data well. Of course, what does it mean to handle data well? I think there are three components to this. First, we need to ensure that data does not overwhelm the components we build in the computing architecture. And we should do it at all layers of the hierarchy. We should do it via intelligent algorithms, via intelligent architectures, and perhaps more importantly going forward, via whole system designs that co-design the algorithm, architecture, and devices together. Second, we should take advantage of vast amounts of data and metadata in the decision-making process that we do in our architectural controllers to improve the architectural and system-level decisions. I'm going to talk about this. Today, we don't do much of this. And third, I think we should build architectures to understand and exploit different properties of different data, such that we can improve not only algorithms, but also underlying architectures in many, many different metrics. And I'm going to give you examples of this also. So based on what I outlined in the previous slide, let me tell you the corollaries that I think in terms of how architectures are dealing with data today. Today's architectures, I think, are terrible at dealing with data because, as I showed you earlier, even though they're called computing devices, they're designed mainly to store and move data and serve the computing units, which are in the end bottlenecked by data. This is because they're processor-centric as opposed to data-centric. And we're going to spend most of the time in this talk on building data-centric architectures. Second, architectures today are terrible at taking advantage of vast amounts of data and metadata available to them. Essentially, they cannot learn. They're designed to make simple decisions, ignoring lots of data. This is because they make human-driven decisions instead of data-driven decisions. So if I look at my cell phone, for example, let's say 5 years old, and my computer, let's say 5 years old, it has a memory controller inside it. This memory controller is taking exactly the same action it has taken in a given state for 5 years. Even though it's seen a lot of data, a lot of workloads, a lot of operating conditions, a lot of different things, a lot of users also potentially, it hasn't learned anything. Even though it could have learned within microseconds very quickly that it could adapt its policy to the executing workload or to the executing operating conditions or something else that's flowing through the memory controller. Essentially, this is very different from humans. As humans, we can learn very quickly. If I put my hand on a hot stove, I can quickly say that I'm not going to do that in that state space. Again, I can generalize from state spaces also. I don't need to exactly measure the temperature of the stove, right? Whereas existing systems build controllers that do not really have this capability of learning. And I think this is a huge deficiency in the design of our systems being intelligent going into the future. I'm not going to have time to talk about this a lot more. That's why I spent a little bit more time over here. But I think a good way forward is really building data-driven architectures that can self-optimize and learn and assess, introspect, essentially, assess the benefits of their actions and change their policies dynamically via learning so that they can take better actions to maximize some metric, maximize some reward function going into the future. Okay, third, architectures today are terrible at knowing and exploiting different properties of different application data. And essentially, in general purpose systems especially, they're designed to treat all data as the same, but even in special purpose systems, underlying architecture does not get communicated a lot of information about data. As a result, they're forced to make component-aware decisions in different components like the memory controller, cache controller, SSD controller, as opposed to data characteristic-aware decisions. Because the very high-level semantic properties of data like compressibility, approximability, error tolerance, error vulnerability, privacy, security, you can imagine many, many things, including even well-studied aspects like locality, are not really communicated to the underlying architecture and hardware. As a result, the hardware cannot really optimize the underlying architecture, underlying decisions that it makes because it doesn't know enough about the data. As a result, it treats all of the data as the same, but this leads to huge inefficiency because clearly not all data is the same. A bit flip that actually destroys your correctness is not the same as a bit flip that's really you don't care much about, of course. So I'm going to also try to talk about this, but we will probably not have much time on that one as well. So let's start with the first one, which is a data-centric approach. I call this data-centric or memory-centric architectures. And in my opinion, a data-centric architecture has at least 4 properties. First of all, it should process data where the data resides, near or in memory structures, or where the data is flowing, essentially where it makes sense to process the data, as opposed to being forced to process the data into something called a processor or an accelerator. Second, synergistically with this, it should really respect data, which means that we need to enable low latency and low energy access to vast amounts of data, not just to caches that are constrained in the processors, but really large-scale main memories, large-scale storage devices. And I think this is really, really important going forward. And to do it at low cost is also important. I don't have time to talk about it, but we do a lot of research in this area that I'm happy to talk about. And this is very synergistic with all of the other properties that I discussed over here, especially the first one. Third, we should clearly enable low-cost data storage and processing. I'm not going to talk much about it. Clearly, this is a focus area going into the future, but there are really interesting technologies that can make it much better. And finally, I'm going to talk a little bit about intelligent data management, which is also required, I believe, for data-centric architecture. We need intelligent controllers handling robustness, security, and cost. I'm going to talk about it to motivate, especially the first one at the top, processing data where it resides. So let's jump into the first one. what does it mean to process data where it makes sense? Basically, we want distributed intelligence across the entire computing system. We should be able to act on the data wherever data resides and wherever data moves, and whenever it makes sense, essentially, as opposed to constraining ourselves to the processor and accelerators. And clearly, this is not a new idea. This is a really old idea, actually. The first paper in the general purpose domain is if you ignore some of the earlier analog computing type of papers that also merge processing and memory, in my opinion. But in the general purpose domain, Harold Stone wrote the first paper that I know of in 1970, doing the research in the late 1960s. And he basically proposes to have a processor close to or inside memory. At that time, it was called the cache. Okay, I'm not going to go through the details of this. There's a lot of really interesting history, clearly, in processing in memory. But this is an idea that has been examined many, many times, but has not panned out. And I believe, so the question is, why should we examine it again today? And we have been examining not today, but for the last 8 years plus or so. And I think today we're in a special place that we have never been before in technology, and as well as applications and systems. Basically, we're constrained between a big push from technology for us to do something different in our memory controllers, and also a big push from applications for us to do something different if you want things to be efficient and higher performance. So I'm going to cover this in a little relatively quickly so that we can go into some of the directions in memory computation. But let me first motivate it from the bottom up, which is push from technology. Today, the DRAM technology is reaching its scaling limits, and it's actually becoming jeopardized. It's having a lot of difficulties. And as a result, there are controllers that are being put close to DRAM. Industry is open to new memory architectures. I'm going to give you examples of this. Clearly, some emerging non-volatile memory architectures are examples of this. I'm not going to talk a lot about that, even though there's a lot of work going on, and we're doing a lot of work also on that. But there are also 3D stacked memory architectures that are more general. It could have DRAM plus logic in different layers. And also there are some experimental architectures that are happening, and I'll point you to some other experimental architectures that actually more commercial architectures that have been produced. So memory scaling is a tough problem. Basically, this is we were talking about this as early as 2011 or so, and I was invited to give this talk at an international memory workshop, where we basically said that memory scaling is going to become much worse, and we need to do something about it. And data-centric architecture design is one of the most important promising directions. At that time, we didn't have a lot of evidence in terms of at least published evidence in terms of the difficulties of memory scaling. But we worked on collecting that evidence. So this is one example of the evidence. Basically, we partnered with Facebook, and we examined all of the memory errors that they have in all of their production data center servers. And this is the graph that we found. Essentially, the chip density that you employ in your memory chip heavily correlates with the server failure rates that you see in your data center servers. And this is a correlational study on running production servers across many, many, many machines. I'm not going to go through more details of this, but essentially, because cells are closer to each other, they're more vulnerable to noise. As a result, you get more errors in more scale technologies. And if you're interested, I'm happy to talk about this. We also built a small-scale infrastructure to understand these scaling problems at a low level and in a more fundamental manner. And we wanted to understand the retention behavior, we wanted to understand the latency behavior, and we wanted to understand different error behaviors. This is our FPGA-based infrastructure that does memory testing. This is another incarnation of it. And we actually released this as an open source to the community. Now, folks in academia and industry are using it, and it has a C++ API, so it's relatively easy to use, and we're happy to support it also. While we were doing these studies, we tested whether DRAM is vulnerable to read disturb errors, and we found out that it is actually. And in existing DRAM chips, you can predictably induce errors in essentially most memory chips. And I'm going to talk about the rowhammer very quickly. Essentially, when we tested the DRAM chips, we found out that more than 80% of the DRAM chips that we tested are vulnerable to read disturb effects, essentially rowhammer. And this is the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. And folks are writing articles that sound like this, essentially, forget software, now hackers are exploiting physics. This is a very nice high-level characterization of rowhammer. So this is a read disturb problem. In a sense, there's nothing new here. But what is new is the read disturb problem gets exposed to the user because technology scaling essentially caused this problem to get exposed to the user. So what is the idea? Essentially, if you actually activate a row, which means apply high voltage to a row in DRAM many, many times consecutively, then you get errors in adjacent rows. So to be able to do that, you need to activate the row, apply high voltage to the word line, and then you need to deactivate, which means pre-charge the bank. And you need to keep doing it. High voltage, low voltage, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage. And if you do it enough times before the cells get refreshed, in many DRAM memory chips, you find out that vulnerable cells in physically adjacent rows actually flip bits. So this clearly should not happen. You should not get data corruption whenever you're just activating a particular row. And we found out that more than 80% of the modules that we tested from 3 major manufacturers are vulnerable. And this is a scaling problem because no chip we tested that was manufactured before 2010 was vulnerable to at least the testing that we have performed. But the vulnerability started in 2010 when cells got too close to each other, and the noise effects of redisturbance because of this hammering, essentially electromagnetic coupling, became too much that you could actually induce these bit flips with a relatively small number of activates you can squeeze into a refresh interval. And you can see that all of the chips that we tested that were manufactured between 2012 and 2013 were vulnerable. Essentially, the cells got too close to each other, and the noise effects have intensified. And there's more. It's not just Rohammer. I'm going to talk about retention as well. So what is the bigger problem with this sort of effect is that it gets exposed to the data structures of the user immediately. As a result, your security is threatened. When we first wrote the paper, we said that memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. I strongly believe this, actually. This is really fundamental for reliable and secure computing going into the future. We said that someone could hijack your computer. And later research, starting with the research from folks at Google Project Zero, showed essentially that. They said that basically they could replicate the problem that we described, and they basically showed that you could take over a system with the beautiful attacks they engineered. And literature is full of attacks that people have designed that take advantage of this sort of bit flips. I'm not going to talk more about this, but the solution direction, in my opinion, is we really need intelligent controllers to fix this. We need intelligence either in the device or the controller, such that we understand this sort of not just attacks, but reliability problems as well, scaling problems, such that we could fix the problem before it gets exposed to the outside. And I'm not going to talk about the details of the solutions. We clearly have published a bunch of solutions, and I'm happy to talk about it separately. But let me tell you where Rohammer is today. So we recently did some studies in 2020, published in 2020, and we showed that memory scaling is actually, this paper is a retrospective on the work that has been done over the course of 6 years. But more recently, we showed that scaling of Rohammer is getting much worse. Essentially, we analyzed more than 1,500 chips, and we found out that newer DRAM chips are much more vulnerable. You could actually induce these bit flips after only 4,800 activates, hammerings, as opposed to 100,000 activates about 8 years ago. So things are becoming much worse. And vulnerability is increasing in different dimensions I'm not going to talk about. And unfortunately, existing mitigation mechanisms are not effective. Either they're not scalable to smaller hammer counts, or they cause significant performance overhead. So there's a lot more work to be done to fix those sort of issues. I believe, again, intelligent controls is necessary. And this is another work that showed that you could circumvent the mitigation techniques that are put into the DRAM devices that are advertised as Rohammer free by the DRAM manufacturers by doing multi-sided or many-sided hammering such that you could overflow the tables of these mitigation mechanisms. I'm not going to talk about this since clearly we don't have time. But the solution, again, in my opinion, is having intelligent controllers to fix these problems and anticipate these issues, even patchable and reconfigurable and programmable memory controllers going into the future, which leads us clearly to doing computation to memory as well. And I'm going to tie that later on. So Rohammer is a very daunting example of the scaling problem in DRAM, but there are other examples that are maybe even more fundamental to the scaling of DRAM, and that's data retention. Can we retain data in memory when we go to very scaled nodes? And clearly, refresh is a performance and energy and quality of service overhead, predictability overhead, and we want to get rid of it. I don't have time to talk about it, but if you want to get rid of refresh, you would like to understand the properties of the different cells, and as well as the properties of different applications that are executing. And you would like to mix and match the application properties to the retention time characteristics of the cells, and also get rid of refresh as much as possible in a fundamental way. I'm not going to talk about this. We've done a lot of research in this area, and you can see that it's still continuing. And I think this, again, based on all of the things that we have seen, you need an intelligent controller to understand the properties of the underlying devices, as well as you need an intelligent controller to be able to communicate with the overlying applications such that you can get rid of refresh as much as possible. Okay, I'm not writing papers. We're not the only ones writing papers about it, clearly, but I'd like to point to this paper that is special from Samsung and Intel. I believe this may be the only paper these two companies that wrote together. We invited them to write a paper to Memory Forum in 2014, where they essentially said what I just said earlier. DRAM process scaling is becoming much worse. Maybe we should be co-architecting controllers and DRAM to enhance the DRAM process scaling. And you can see that going into the future, emerging non-volatile memory technologies require intelligent memory controllers as well. So hybrid memory systems is a very promising direction going into the future, whether you have different types of DRAM or different types of technology. Every technology or every different type of memory you have has some greens and has some reds. And the key idea is to maximize the greens as much as possible by doing intelligent data allocation and mapping, while minimizing the reds of each technology as much as possible. To be able to do that, I don't see any other way than having an intelligent controller that understands the characteristics of these technologies and that understands the characteristics of the data that's coming to it from the applications, and that's essentially matches them so that you get the best of multiple worlds over here. Okay, so that was the end of the push from technology part for me. I'm going to now motivate things from applications and system side, and that's going to be also important, if not more important than the technology side. Today, in applications, we're very much bottlenecked by data access. Energy consumption is a key limiter, and data movement energy dominates compute energy, especially for off-chip to on-chip movement today. So in my mind, the question looks like this. Basically, do we want a sustainable world going into the future, very sustainable, which requires us to be very energy efficient? Or do we want a world where we cannot breathe, but maybe extremely productive? I would argue that we want the best of both worlds. Essentially, we certainly want sustainability and energy efficiency, but we also want high performance and high productivity at the highest level so that we can solve the most challenging problems that we're faced going into the future. So let's see how we're dealing with it. Essentially, today, data access is the major performance and energy bottleneck, but our current design principles go directly against what we want, as I described in the previous slide. They cause great energy waste, leading to energy and sustainability problems. And they also cause great performance loss, leading to both low performance as well as sustainability and energy problems. I put this performance loss in parentheses because clearly data access has large energy waste and large latency. And we do a lot in our systems to overcome the latency overhead of data access. We actually complicate our systems, both software and hardware, as well as system design, to add many, many mechanisms. Examples include massive multi-threading, large levels of out-of-order execution, many, many hierarchies of caching at both software and hardware levels, as well as prefetching mechanisms, again, at both software and hardware levels. So we try very, very hard to overcome the performance loss of data access because we have a processor-centric design. But we still have performance loss because these techniques do not work perfectly. And whenever they are not effective in the applications, they cause additional complexity, a lot of complexity, and even more energy waste. So today we're in a vicious cycle. Data access causes great energy waste. To overcome the data access latency, we actually add a lot more complexity, which causes even more great energy waste. So we keep going in this vicious cycle. And I don't think we have a good way of breaking the vicious cycle unless we understand where the problem is. And the heart of the problem lies in the fact that we're very processor-centric. Essentially, we're processing data far away from the data, and processor is the only place where data is processed. And we're back to the picture that I showed you earlier. We've heavily optimized the computing unit. Everything else is there to serve the processor. And as a result, we're back to the earlier picture that I showed you, where we're extremely complex, low energy inefficient, and also low performance, as I will show you in a little bit. Yet we know that memory clearly is a bottleneck. So this is not news clearly to many people over here. This is a quote from Dick Seitz, who was the chief architect of Alpha architectures. And after his team designed a flagship Alpha processor in the 1990s, he basically wrote this microprocessor report article, which is one page, which he titled, "It's the Memory Stupid." Basically, he said in this article that we designed this processor to finish one instructions every 4 cycles, 4 instructions per cycle. But it's finishing one instruction every 4.5 to 4.7 cycles in this important data-intensive workload, which means that it's operating at 1/16th to 1/20th of its peak bandwidth. And why? Because it's waiting for data to come back from memory. And essentially, he finished the article saying that I expect over the coming decade, memory subsystem design will be the only emphasis on him. Important design issue for microprocessors. And I agree with this. I think there's a lot more to be done because we haven't explored what we can achieve with the memory and storage to get combined with compute technology going into the future. So 10 years later, I did this work in my PhD thesis, and we essentially partnered with Intel and showed that in the workloads that they use to design their processors with, the memory intensive ones, more than 50% of the time, the processor is waiting for data to come back from main memory. Okay, you don't believe me, you don't believe DeepSites. Since many people believe Google today, I'll give you data from Google. And essentially, Google showed in this beautiful ISCA 2015 paper, across all of their data center workloads, that a state-of-the-art processor that they employ in their data centers is waiting for data most of the time. It's doing useful work only 10 to 20% of the time. And they have, I'd recommend looking into this paper. There's a lot of microarchitectural analysis of the workload. So basically, this happens because processor-centric. We have a grossly imbalanced computing system. Every processing is done only in one place, and everything else just stores and moves data. As a result, data moves a lot, and the processor waits. This is energy inefficient, low performance, and complex. And to tolerate this, we design our systems and processors to be overly complex and bloated, as well as accelerators, of course. This leads to complex hierarchies and mechanisms, but this is energy inefficient, complex, and low performance because we could have used all of that effort as well as the real estate for something else that improves performance. As a result, we're back to the picture that I showed you earlier, where we have a compute and storage, where we have, instead of a computing system, we have a data storage and movement system. Most of the real estate is dedicated to that. Let me give you the energy perspective quickly also. This is a slide that I borrowed from Bill Daly from his high-peak keynote, where he analyzed the cost of different operations. Essentially, a 64-bit double precision floating point operation at the time is 20 picojoules. You could clearly optimize it today, much more. But a DRAM read or write is 16 nanojoules. You could also clearly optimize it today, much more. But if you take away these numbers, it's 800x. But today, we're somewhere between 2 to 3 orders of magnitude in terms of the energy consumption of a memory access compared to the energy consumption of a complex or simple addition. And you can read more papers that talk about this. We have written some papers on it too. So basically, that's why we have this picture. More than 60% of the total system energy end-to-end on real applications is spent on data movement. I would argue that we do not want to move data. Essentially, to be able to do that, we need to change the paradigm and mindset we have. We want to enable computation with minimal data movement. We want to compute where it makes sense, where data resides. And this requires us to make computing architectures and also our thinking much more data-centric as opposed to processor-centric. So I'm going to give you a specialized example of data-centric design, focusing a lot on main memory. But as I said, this requires distributed intelligence across all of our components. You want processing inside the cache. You want processing inside the SSD. You want processing inside the tape, perhaps. You want processing inside the interconnect. Basically, we want processing everywhere. But I'm going to focus on memory because memory is clearly very interesting and potentially one of the hardest places to do this. But what memory enables is a very large-scale storage of some really important applications like in-memory databases, in-memory graph processing, in-memory media processing. People have took the pains to actually do some of these applications inside the memory so that they don't need to access the SSDs or storage as much as possible. But of course, that doesn't always work clearly. So what we would like to be able to do is we'd like to be able to query memory, ask questions, memory, can you execute this function for me? And the memory responds with results if it can. That's the idea, basically. We want the intelligence side of memory. So there are clearly many, many questions over here that span across the stack. How do we design the memory and controllers, the processor chip and in-memory units, software and hardware interfaces, none of which really exist today in the way we want, system software compilers and languages such that we can enable this in a general purpose manner and make life easy and get more efficiency, and algorithms and also theoretical foundations of computing when we have this sort of computation. I'm going to talk about this briefly. Basically, this is a problem that spans all the way from algorithms to devices, and sometimes you would like to really design your algorithms to match the behavior of the devices. And I think very quickly, today's computer science foundations are really based on the processor-centric mindset and paradigm. Essentially, we're counting operations. If you look at the big O notation, big data notation, complexity theory, it's all about counting operations. It really does not consider a data-centric view, which is really memory being the bottleneck, and should we do something different in our system? So we really need to overhaul the theoretical foundations of computing going into the future as well to incorporate data-centric paradigms. Okay, that said, let's talk about some approaches to processing in memory that I consider interesting and important going into the future. As I said, some approaches have been examined, but most of the approaches that have been examined in the past 40 years or so is really about, okay, can I take a processor and put it inside the memory chip? I think it has some merits clearly, but this is not going to be as easy. Clearly, processing and DRAM or any type of some other types of memory do not have good fabrication capabilities together. You don't get best in processing as well as best in memory when you fabricate these things together. So I think that approach is going to be still interesting, but maybe it's not going to be as easy as what I'm going to describe in the next next part of the talk. And the two things that I'm going to describe is minimally changing memory chips by exploiting the analog computation and data movement capability inside the memory chips. And the second is exploiting technology advances like 3D stacked memory such that we can put computation close to memory. The first one is also called processing using the memory, such that you use the capabilities of the storage device as a compute device. And the second is more like processing near memory. You push compute near the memory as opposed to inside the device itself. Okay, so let's start with the first one. I'm going to give you examples a lot from DRAM, but actually all of these generalize to other memory technologies like phase change memory, STT-MRAM, etc. I'm not going to talk about those in detail, but we do work in that area and I'm happy to talk about it. Essentially, any memory has great capability to perform bulk data movement and computation internally with small changes. You can exploit internal connectivity to move data inside the memory. You can exploit the analog computation capability that it's given to you by the operational principles of the memory. And on top of this, you can add more internal connectivity to make it closer to maybe like a brain-like system, let's say better internal connectivity, or you can add even more computation capability as well. Of course, that comes at a cost, clearly, both of them. So I'm going to give you some examples over here. I'm going to start by cheating. I'm not going to even talk about computation first. I'm going to talk about data copy and initialization. And this is important because clearly data copy and initialization is used by many, many, many workloads in the system. So I'll give you the example of a 1 terabyte database, and I want to initialize it. How long does it take? I actually give this to my students in the courses. Clearly, if you want to initialize a database, it's going to take long. Does it make sense to do it the way we're doing it today? Okay, clearly, Google also showed that data copy initialization is really important. In the same paper that I mentioned earlier in ISCA 2015, they said that just these two system calls, memmove and memcopy, are responsible for approximately 5% of the execution cycles on all of their workloads in Google's data center. It's surprising to see just two function system calls that are doing copying of data to be responsible. This shows that copying is so important. Even initialization is not included in these function calls in many cases. And there are other cases where you do data copy that do not go through these function calls clearly. Okay, so how do we do data copy in our systems today? Because we're processor-centric, if you want to copy a source page to a destination page today, white page to the gray page, we bring the data into the processor for both pages, and then we write back the data. So clear, this is high latency. This is high bandwidth utilization on the memory bus, which is perhaps the most bandwidth constrained resource we have in the system. This causes cache pollution if you don't do it through the direct memory access engine over here. And this causes a lot of unwanted data movement. We'd like to get rid of all of this. Today, for a 4 kilobyte page copy, small page copy, done through direct memory access, it consumes about 1,000 nanoseconds and 3.6 microjoules. Now, if you show this picture to someone who is not initiated, let's say a 10-year-old child, and say, can I do this better? Maybe they will point you to the direction of, why don't we just do it in memory? And that's the idea, basically. The idea is very simple. If you do it in memory, it'll be low latency. Clearly, you won't exercise these long latency interconnects. It will be no bandwidth utilization, no data bus utilization on the memory bus, no cache pollution, but you could eliminate that today anyway, and no unwanted data mode. So we're going to exploit the high bandwidth, low latency internal connectivity inside the banks, inside the subarray, such that we can reduce the 1,000 nanoseconds to about 90 nanoseconds unoptimized, and 3.6 microjoules to 0.04 microjoules unoptimized. And the basic idea is very simple. I'm going to give you the example of copying data within a subarray, and that's the fastest version of it. So if you look at a DRAM subarray, different rows are connected to a row buffer, which are the sense amplifiers, and we're going to use the row buffer as a temporary buffer to copy data from one row to another. And to be able to do that, we first activate the source row, which brings the data into the row buffer, and then we activate the destination row, which implicitly activates the source row, but the data stays in the row buffer. And then when we activate the destination row, the sense amplifiers, the row buffer, drives its data back into the row B over here, the destination row. So by doing 2 consecutive activates with negligible hardware costs, you can get more than 10x improvement in latency and more than 70x improvement in memory energy. I'm going to get back to this in a little bit. Clearly, by increasing the interconnectivity in the DRAM chip, you can get closer to this red bar whenever you move data inside the bank, as well as inside the across the subarrays and across different banks. We have some works in this area that show that by increasing the connectivity inside DRAM, you get closer to this red bar, and you can actually move data relatively efficiently across the entire DRAM chip. But I'm not going to talk about those in this talk. So basically, the thinking we have is memory is a specialized accelerator. Similar to many, many other specialized accelerators we built, it does what it does best. And copying data, initializing data is an example of what it does best. But this accelerator is very special also because it's sitting on the right side of the memory bus as opposed to the left side of the memory bus. Every other accelerator is bottlenecked by memory. This accelerator is not. And this accelerator has low latency, high bandwidth, low energy access to vast amounts of memory that it's co-designed with or that is sitting next to. So, okay, I cheated. Now I'm going to give you some computation as well. We actually can support in-memory bulk bitwise operations and or not and majority at low cost by using the analog computation capability of DRAM. But this idea is also applicable to NVM, as other works have shown. And the key idea is to activate multiple rows concurrently, and that performs computation due to the charge sharing principles with which DRAM operates. And this leads to 30 to 60x performance energy improvement on many bulk bitwise operations. I'm going to briefly cover them. But I believe new memory technologies enable even more opportunities. These resistive memory technologies, because they're resistive and non-volatile, they actually can operate on data with minimal data movement. And they don't need to, because the reads are not destructive in these technologies, your data movement can be minimized even more. In addition, these technologies have crossbar array structure, and they can do specialized matrix vector multiplication in the crossbar array structure, which I'm not going to talk about. But let's focus on DRAM and triple row activation. So basically, I'm going to introduce the primitive of triple row activation. You have these 3 rows, A, B, C. I'm showing 1 bit. Imagine 8 kilobytes in each row. And imagine doing this in 1,000 different subarrays. So you have 8 million bits at the same time that you're operating in. So basically, if we're concurrently activate A, B, C over here, what happens is, due to charge sharing principles, if at least 2 cells are charged, you get the charge state at the end. If at least 2 cells are discharged, you get the discharge state at the end. So basically, you have a bitwise majority function, which is a beautiful function. And actually, you can map many algorithms to bitwise majority functions such that you can implement the algorithms. In fact, there's a lot of interesting work going on in PFL in Nani's group that show that you can map Boolean logic to logic synthesis using majority functions. I'm not going to talk about that. We actually have some work coming up in ASPLOS that looks at how can we change the programming model such that we can map things much more efficiently to bitwise majority functions. But if you actually realize, if you rewrite this Boolean equation, you take by taking out C. If C is 1, you get the OR of A and B. If C is 0, you get the AND of A and B. So we have a bitwise AND and bitwise NOT that we can do across millions of bits in the DRAM. So you can expose this to the instruction set architecture. I'm not going to go through this in detail, but basically to minimize the implementation cost, you need to do this triple row activation in a special place in memory. You cannot do it across the entire array. That's a mess to design. And if you actually need to do that, you need to combine row clone and triple row activate in some way such that you can translate this ISA instruction to these smaller primitives that you actually execute in memory. And of course, and OR are great, but unfortunately, they're not functionally complete. To enable functional completeness, we need a NOT, and we have that NOT. In fact, in our DRAM chips today, if you actually activate a cell, activate a row, the complement of the cell or the row is on the other side of the sense amplifiers, which are not connected anywhere. Actually, they're connected to the other side of the subarray, other subarray. But basically, we want to take that value and feed it back into the subarray, such that we can get the complement of a cell. And we do that using a special row and special type of cell. I'm not going to go through the details, but essentially you can implement NOT with some overhead, which is more overhead than AND and OR, but still less than 1% of the DRAM chip area. And that way you can get significant performance energy reductions in NOT. You can see close to 60x. And 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 OR are quite good also. And you can build higher level primitives on top of this, including algorithms that take advantage of all of this clearly. So clearly, if you know what you're doing, if you know your algorithm well, and with some effort, you can map your algorithm to these underlying bulk bitwise operations. But there are some algorithms and also applications that are already been written in a manner that are more amenable to these bulk bitwise operations. And I'm going to examine them very, very quickly. Bitmap indices and databases are examples. They operate on huge bitmaps. Bitweaving is a database that's written specially for maximizing the bitwise operations that are done in databases. Bitfunnel is Microsoft's web search engine. It's written in a similar fashion for the same purpose, maximizing bitwise operations so that they can execute the web search and database in the better in the GPUs. DNA sequence mapping, encryption set operations, I'm happy to talk about those separately. But we actually took bitmap indices, for example, several databases, and we did an end-to-end design manually, completely, such that we could execute these bitmap indices on our substrate, bulk bitwise substrate called Ambit. And we found out that on many queries, you get more than 5 to 6x latency reduction, execution time, end-to-end execution time reduction, which I believe is promising. And we didn't quite optimize the system. I think there's more to optimize the system. For example, later work showed that you could actually optimize some of the operations that we have to minimize the majority function calculations, etc. I'm not going to go through that in detail. We also took this database that's specially designed for maximizing bitwise operations, the Bitweaving database, and we poured it to Ambit as well. And we saw even more performance improvements on some queries. You get to 12x over here, for example. And the good thing is that your performance improvement increases with the size of the database that you have. Of course, at some point you saturate because you cannot, you don't have enough rows in your DRAM chip. But until you saturate, your performance improvement increases. So if you're more interested in this, we've written papers about this topic, and this is the fundamental paper that covers all of them. And we recently written this book chapter that talks more about the future directions and some of the challenges going to the future. Now, this work, after we have done and completely independently of us, they've shown that you can essentially imitate row clone and bitwise operations as we described them in off-the-shelf DRAM by modifying the memory controller. So they took the soft-MC infrastructure that we built, as I discussed earlier. They basically changed the timing parameters to access main memory, and they were able to imitate back-to-back activates in row clone. And in many chips, they saw reliable copying of data. And in some chips, they were able to replicate that by changing the timing parameters very, very carefully, of course. You could do bitwise and or operations in a bulk bitwise manner, just like we described. So this basically shows that existing DRAM chips, without any modification to the chip itself, just by modifying the memory controller, you are capable of doing copying and computation, as we discussed. This is a proof of concept, clearly. To be able to do this reliably, you need to change the chip. But imagine what you could do if you are able to change the chip and put computation inside the memory in the manner we described in a reliable fashion. So other works also show that you could do this sort of bulk bitwise operations in non-volatile memory technologies like PCM, etc. And they also show that on graph processing and machine learning workloads using these operations, you could get significant performance and energy improvements. Okay, so this is clearly an exciting direction. I think there's a lot more work to do, and we're doing a lot more work in this area. But let me switch to some other opportunistic direction, which is exploiting 3D stacked memory. So 3D stacked logic and memory today exists in some form. You have memory layers on top of logic layer. And in the logic layer, you can put computation clearly. And the computation elements that you have over there can operate very quickly on the memory layers on top of them. And other true three-dimensional technologies under development, I actually like the monolithic three-dimensional technologies quite a bit. The next project at Stanford is developing very interesting technologies, and we actually have some work going on in that area in understanding applications and architectures when monolithic three-dimensional technologies occur. But this is an extension of 3D stacking, in my opinion, going into the future and making it more capable going into the future. And clearly, 3D stacked memory technologies existed for a while. This is based on the Ramulator paper that we've written, we released to the community. Again, this is another DRAM simulator that we maintain, and we work together with industry and academia to enable research in DRAM. So when we started doing research in 3D stack processing in memory, we asked basically two key questions, and I'm going to cover both of them. Basically, first of all, what if we had the entire freedom in the world to change everything possible in the system? What kind of benefits would we get on acceleration of some workloads? And then being more realistic, what if we can do a simple functional floating? And then we actually go to the opposite end, which is what is the minimal thing that we can do with minimal change to the system and programming so that we can do it, it can take advantage of 3D stack processing in memory. I'm going to talk about these relatively quickly. Let me talk about the first one. What if you had the entire freedom in the system and you were able to specialize your system some particular applications and get rid of some of the programming and coherence and virtual memory requirements, let's say. Now, if you do, we wanted to focus on graph processing. Clearly, graph processing is very, very interesting today, going into the future as well. A lot of bioinformatics is increasingly based on graph processing. A lot of machine learning frameworks are based on graph processing. But if you look at graph processing, if you throw cores at the problem, you don't get as much speed up, but you get a lot of energy and efficiency. And the main reason is at the core of many graph processing algorithms, you have a good chunk of random memory accesses and little amount of computation. So you really exercise the memory, energy, and performance bottlenecks because you don't have a whole lot of locality in many parts of the algorithm. And you cannot cover for it because you don't have a lot of computation as well. So to essentially build an accelerator for graph processing with 3D stacked memory plus logic chips, we designed what's called Tesseract. I'm going to go through it at a very high level. There's a lot more detail in the paper that I referenced at the bottom over here. But basically, we start with this 3D stacked memory plus logic chip. In the logic layer, you see this chip is divided into what's called vaults. Each vault is connected to each other with some network. And the vault has a DRAM controller that controls the memory stack on top of it. And we basically add in-order cores to these vaults such that we can do processing on the inside the vault itself. And processing is done in a message passing manner. Basically, whenever a vault needs to update a graph node, it needs to send a message to the vault that houses that graph node in its memory layers. So essentially, it's a remote function call, remote procedure call based programming model similar to distributed systems. And we do the updates in place locally, but of course, intermediate data needs to be moved. but that data is not a whole lot, as we show in the paper. Basically, to scale up this system, you need to add more 3D stack logic and memory chips, as you can see, with some sort of interconnect. We use Dragonfly in this case, but clearly, and then you connect this distributed processing unit to a host processor and use it as an accelerator, a very primitive form of GPU. You can see that it's non-cacheable, physically addressed. There's no virtual memory. We get rid of coherence because it's message passing based, and we change the programming model also. But basically, to take advantage of this, you need to partition your graph nicely such that you don't exercise these off-chip links as much as possible. And you also minimize the interconnect communication within the vault as well. So you need to be careful about what you're doing. And we did our best. Basically, I'm going to show you some results related to it. Basically, well, our best meaning, we didn't extremely optimize it. I'm going to, other works actually optimize it later on. But basically, Tesseract looks different from existing systems because it's it doesn't have the compute plus memory dichotomy. Both are together. And as a result, you expose 8 terabytes per second to all of the compute units over here together. But remember, this is data from 2013 or 2014. Today, this will be higher. Today, this will also be higher, clearly. This is the conventional system that we evaluate against when we wrote the paper. But basically, if you do all of this on 5 graph processing algorithms, you get more than 13x performance improvement. And we didn't optimize the system heavily. Later works showed that by doing better scheduling, better data partitioning, better graph partitioning, a better optimization of how you actually move the data, you could actually get to 2 orders of magnitude compared to the best baseline, best compute-centric baseline. I'm not going to go through this in more detail, but we also showed significant energy benefits. Again, this is 8x when we wrote the paper. Existing work that improved upon our work shows that it's closer to 2 orders of magnitude. Okay, so that was changing the entire system. Clearly, this may be interesting to some folks who are really interested in getting the performance and energy efficiency out of it, just like how GPUs evolved over time. But clearly, this is not a general purpose machine that could be interesting to everyone in the world. So later, we started looking into function offloading as a method of getting performance out of the 3D stack processing in memory. And I'm going to talk about this paper that I mentioned briefly, which this is the work we did with Google over the course of 1.5 years, where we analyzed energy consumption in consumer devices. And we especially analyzed these 4 important workloads that I believe everybody is using some version of, not necessarily Google's version, clearly, but many other versions exist. And we quantified the energy cost of data movement in these mobile systems. And we found out that more than 60% of the total system energy is spent on data movement across the hierarchy. And we wanted to understand the benefits of moving computation close to data. The challenge here is really limited area and energy budgets. So you really need to be careful what you put into the logic layer, because terminals are also problematic. So basically, the second key observation helps that. We found out that a significant fraction of the data movement often comes from simple functions, and you can implement these simple functions either in low power embedded cores or fixed function accelerators. In my opinion, both of them are good, and adding more reconfigurable logic is also a good idea going into the future. So the takeaway is you get about 2x performance improvement and 2x energy improvement if you actually do what I just discussed. This is not 13x, this is not 100x clearly, it's not 60x like what we discussed with Ambit, but it's not bad also because it's not really changing a whole lot in the system. It's just identifying the functions and offloading them. In fact, we have some recent work that's going to be published in Sigmetrics in 2021, where we analyzed more than 300 workloads and try to understand the characteristics of different functions that should be offloaded to main memory. And we're looking into that analysis, and we'd be happy to talk about that going into the future. Let me quickly show you examples of these functions. I'm not going to go into a lot of detail since we don't have time, but from TensorFlow, for example, Google's inference framework, most of the energy is spent on data movement, and 2 functions are responsible for a good chunk of that energy: packing and unpacking of the data, such that you prepare the data for efficient processing for the next layer, and quantization of the data such that you improve the efficiency of processing of the data. I'm not going to go through these, but both of these functions, packing and unpacking and quantization, are simple processes that require simple arithmetic operations that fit really well into the logic layer of memory. And if you actually offload them, you get significant performance and energy benefits. This is the energy benefit over here. And if you have a specialized accelerator doing it, you get even more benefit, as you can see over here. And you can see similar functions in the Chrome browser: compression, decompression, etc. And in the video playback and capture, motion estimation is one example. Clearly, this is already employed in hardware accelerators for video playback, but moving it to the memory has significant benefits compared to keeping it on the compute side. Okay, so I've said enough about function offloading. There's clearly more about function offloading. We
have 5 more minutes until the question, the Q&A.
Okay. Part. Okay, great. Yeah, I should be able to be done plus perhaps plus 1 minute. Okay, so basically, we did a lot of work on GPUs. I'm happy to talk about that separately. Extracting linked data structure is very interesting, I think. Dependent cache misses. Extracting prefetching mechanism is interesting. And more recently, we have examined extracting stencils in real systems like FPGA systems that employ high bandwidth memory, which is a way toward processing in the logic layer clearly. And I mentioned this work on genome analysis earlier. Okay, so let me talk about the minimal thing, and then I'm going to conclude. We don't have time to do other things. Basically, very quickly, what if you had to change the system minimally to take advantage of processing in memory? And the idea over here is, if you want to do that, you would like to expose the processing in memory operations as processor instructions that are executed just like any other processor instruction. They're virtually addressed, they're cache coherent, they operate on a single cache block. That's the idea. And the processor decides where to execute them. So this could be PIM-add, for example, and the programmer can use them, compiler can generate them. There's no changes to the sequential execution and programming model, no changes to virtual memory, minimal changes to cache coherence, and no need for careful data mapping such that your data appears to be in the same place if for in-memory processing. And the second key idea is to dynamically decide where to execute this PIM-enabled instruction, and there are heuristics here in the paper that can be improved going into the future. So this is an example from the PageRank application that I showed you earlier, this PIM-add, but there are also other sophisticated instructions that we added, like dot product to enable machine learning better, Euclidean distance to enable time series analysis better, histogram bin indexing, hash table quoting, ... You can see more in the paper. I believe customizable ISAs combined with a reconfigurable logic layer is a very good fit for enabling systems to execute this sort of specialized instruction going into the future. And the performance benefits and energy benefits are actually reasonably well, given the effort. We get basically 47% performance improvement on large input data sets and 25% energy reduction on a single node, again, on the large input data sets. And I think this is a more adaptable version of processing in memory. Let me quickly talk about the adoption barriers of processing in memory, because whenever you try to change the paradigm or come up with a complete new hardware design, or system design, you need to tackle the barriers to adoption. And these are the 5 barriers to adoption. Most of them are related to systems and software. The first one is functionality of an application and software for PIM. This is hardware-software co-design, clearly. What should we do, basically? The second is ease of programming. What kind of interfaces are exposed? What kind of component hardware support should we provide? What kind of system support should we provide? Coherence and virtual memory, how do we handle it? How do we design the runtime and compilation system for adaptive scheduling, data mapping, access control, security, etc.? And how do we design infrastructures to assess benefits and feasibility of what we're doing? I think all of these are clearly challenges, and those challenges also existed for something like GPUs, for example, that have changed systems quite a bit. I believe all can be solved with a change of mindset. I think if we think in a data-centric manner and take step by step, we can solve these challenges. So we need to revisit the entire stack in the end, all algorithm to devices, but I believe we can get there step by step. And these are some papers that we've written on processing in memory review and open problems. If you're interested, I'm happy to talk about them. So UPMEM has a processing in DRAM engine that fits neither of the criteria that I showed you earlier. Essentially, they put a processing engine next to each bank, and you can do a sophisticated operation on this processing engine. And we're actually working with them to understand the real hardware that they've designed. I'm happy to talk about that separately also. So let me quickly cover these papers just in skipping slides. There's a lot of work in this area, and we'd be happy to support the work also with the infrastructure that we've developed. But the big challenge and opportunity for the future is designing computing architectures with minimal data movement. As I said, I'm not going to talk about the data-driven and data-aware aspects. I left the slides over here so that people can, if they're interested, look at the slides, and I'm happy to answer questions. These are directions that are going on in my group to design much more self-optimizing computing architectures, and architectures that can actually understand the semantic properties of the data and act much better based on those semantic properties, which we call data-aware architectures. So, and I think these 3 things actually are synergistic with each other. If you want to build a data-centric system, you also want to be data-aware. If you want to build a data-driven system, you want to be data-centric and data-aware at the same time. So these 3 things actually interact with each other in very, very interesting ways. And if you actually build them all together, I believe you have a multiplicative factor in terms of performance and energy. So let me conclude here. I believe it's time to design principled system architectures to solve the data handling problem, which manifests itself as a memory and storage problem today because of the way we design our systems. We need to design complete systems to be truly balanced, high performance, energy efficient, which will hopefully lead us to more intelligent architectures that are data-centric, data-driven, and data-aware. I believe a fundamental component is to enable computation capability inside and close to memory and have everything as distributed intelligent agents. I believe this can lead to orders of magnitude improvements, as I've shown you examples of in this talk, enable new applications and computing platforms like genomic analysis platforms that anybody can have in their hand and do genome analysis analysis privately and also at very high speeds. Enable better understanding of the nature as well going into the future. This was also mentioned in an earlier keynote, I think, where I believe we can understand, maybe we don't understand the nature today, but if your compute models are actually closer to the nature, maybe we can understand it better. I believe for that we need data-centric, data-driven, and data-aware. I don't claim to know exactly how this thing operates over here, and I'm not sure we should really imitate it in everything it does, but we should perhaps imitate it in some things it does. I know for sure that this is not a processor-centric engine, and but we are today designing things to be processor-centric. I believe to get there, we need to revisit the entire stack, and this may be a daunting problem. And this may require changing our educational systems, which I strongly believe in. I believe we need to really cover algorithms to devices in our educational systems as opposed to creating silos in between. But I believe we should also, we're not going to get to the general purpose systems overnight, perhaps, but we could enable progress by taking things step by step. For example, implementing things like row clone, implementing things like ambit, simple operations that minimally change the memory systems, or implementing things like very simple instructions that can be executed on the memory side. So I believe there are a lot of good principles that we need to discover and exploit. These are some of the principles that I did not call out. Well, some of them I called out, but not all of them I called out. And I think these principles are good principles to exploit going into the future, and there may be more principles as well. But I think perhaps the most important principle is keeping our minds open, because I believe the biggest thing that hinders our progress is the thinking that goes on in a processor-centric manner. Everything that we design in our systems today has its imprints on, has the processor-centric design paradigms imprints on it. As a result, we need to somehow change the playing field such that we think in a data-centric manner. And I gave you the example of theoretical foundation of computing as one example of this, and the memory control as another example. So these are the papers that I mentioned that are overview of processing in memory. And there's a longer version of this talk also that was delivered relatively recently. If you're interested in learning more about the data-aware and data-driven parts, there's more detail over there in this talk. I've also acknowledged people who fund our research. Please keep funding us. We'd be happy to share our results. And I will most importantly acknowledge my students, postdocs, and collaborators in my research group. They are the reason why I'm here and speaking about all of their work today. So with that, I will conclude. Thank you very much for bearing with me. I'd be happy to take questions.